to fix problems, we have to better understand them.
How do you protect your communities, your people, your infrastructure, your commerce? How do you protect your tourism industry? All these things, are essential to just being able to function and live on the coast.
Outside of COVID-19, my 5 biggest challenges are drug abuse and addiction, it's crumbling infrastructure, it's degraded water quality, it's the effects of climate change, and the 5th one, and maybe the most profound, is an expanding socioeconomic divide that we knew existed. Florence exposed it, Dorian widened it, and now the pandemic is widening it and deepening it even more.
We're in a situation this year where we're thinking about what it would mean to evacuate people under conditions where we're trying to maintain social distancing. I think that's a challenge in and of itself.
There's knowledge that local governments as well as our citizens have that is important in developing the long-term solutions that community will ultimately pay for.
We want to pull from the resources that we have available to be able to handle some of these massive challenges that we have. And Seacoast offers that opportunity for us.
Seacoast is really about collaboration. It's about bringing together a wide range of perspectives and expertise to identify what we need to know to support long-term coastal resilience, and then working together to build a research program around that.
When you give the community a chance to have buy-in to the solutions that resolve problems in their community, then they become champions for the cause.
We know that we can't hold back Mother Nature. She's a lot more powerful than we are. So we have to adapt. And doing that in a way that makes sense, socially and financially, is, to me, that's what coastal resilience is all about.
The purpose of the first session of Disciplines 101 today is to provide scientific scaffolding to facilitate interdisciplinary and transdisciplinary collaboration throughout the project. Megan Mullen, an associate professor of environmental politics at Duke, and Martin Smith, professor of environmental economics at Duke, will make connections between 2 different activities in social science and policy and illustrate these connections with examples from coastal policy. Dylan McNamara, professor of physics and physical oceanography at UNC Wilmington and an expert in nonlinear dynamics, will introduce the language, theories, and methods of nonlinear dynamics that are central to the core questions Seacoast seeks to investigate, and he will provide examples from coastal systems. Please note there will be a 10 minutes for questions and answer Q&A session after each talk. And please submit your questions within the chat. The questions will go directly to Seacoast Project Manager Catherine Anardi, who will moderate the Q&A. And if your question is for a particular speaker, please help us out by indicating which speaker your question is directed at in the beginning of your question as you post it in the chat. And with that, I'm going to turn the screen and the mic, so to speak, over to Marty Smith. Thank you all for being here.
Hi, everyone. I think Megan is going to start us off.
Megan, I think
Megan,
you
you're
need to
muted.
unmute.
Pass.
Classic. Thanks, everybody. We're going to start by giving you a view into the conversations that Marty and I have on the front porch. Marty, you always like to talk about the optimal policy and first best policy, but that presumes everyone agrees with your objective to maximize efficiency.
Megan, I could say, what's wrong with efficiency? But really, the problem is that you are unwilling to specify an alternative objective. You tell me what that is, We can optimize it to find the first best policy.
Efficiency is just one of many objectives that might matter when we think about policies. So you might claim that a policy is optimal because it has the highest benefit cost ratio, but the same policy might lead to concentrated benefits for the rich and concentrated costs for the poor.
Well, if equity matters, then we might consider a second best policy that is almost as efficient, but that leads to more equitable outcomes.
But then we need to define equity. Is that equal distributions of resources? Is it improving outcomes for the least well off? Even if you're open-minded about other policies, you're still using this first best language that implicitly privileges efficiency over equity and other outcomes.
The efficient policy is a natural starting place because it allows us to think about how much society is giving up in order to pursue some of these other objectives. There's only so much tax that the political system will allow governments to collect, and that will limit how much can be spent on things like regulations and public projects. So how would you decide what policy to recommend?
Well, that's where politics comes in. Society would somehow have to engage in collective decision-making to define its long-term goals.
And I'll be waiting.
So these are conversations that we have across social science disciplines about the normative values that undergird our work and how those normative values translate into positive theory and positive empirical research. And these conversations aren't new. They've occupied social scientists for more than a century. John Neville offered definitions that still guide these conversations today. A positive science can be defined as a body of systematized knowledge concerning what is. A normative science as a body of systematized knowledge pertaining to criteria of what ought to be and concerned with distinguishing the ideal from the actual. And art, he said, is a system of rules for the attainment of a given end. And to Keynes, art specifically meant applied economics. It's the translation of normative goals and positive theory to ask research questions about how some lever, which is often a government policy, can produce an outcome. And this positive normative distinction and how we navigate it is present across the social sciences. All social sciences include some positive and some normative research. And the social sciences vary across disciplines, also over time. And the dominance of either positive or normative research over the other, the barrier between these bodies of work and how much they're in conversation with one another. Each discipline has normative topics that tend to be of interest, but the disciplines vary in how much within discipline agreement there is about those normative interests. So in that conversation, you heard that in economics, there tends to be a lot of agreement about what the normative focus for policies might be. In political science, there's a lot more variability in what we're concentrating on. And disciplines that have more widely shared normative commitments tend to be more willing to prescribe policy or other actions.
So I'm going to talk briefly about an example. Many of you who work in the coastal space are familiar with beach nourishment. This is an engineering intervention to address eroding beaches and in many cases defend shoreline and maintain a wide beach for recreation. It's obviously a policy that's not without controversy, and no one is claiming that this is the solution or even a solution to very long run problems. I want to use this to illustrate some of the different types of questions that economists ask and answer, and then Megan will do the same for political scientists. So a normative set of questions in economics might be something like, should community A nourish its beach? Should this community go out, dredge sand, and rebuild an eroded beach? A related question is whether the federal government should actually subsidize local nourishment. There may be some reason locally that the money is not available, but it's still a good policy potentially. And similarly, how long should communities continue to nourish their beaches? When should they give up this practice? Now, to distinguish these, we might think about very different types of questions in the positive sphere. And these might have to do with the mechanisms embedded in why communities do what they do, including things like how do property values affect the decision to nourish, or turning that around another way, how does nourishment affect property values? If the cost of nourishment CN rose by a certain amount, say X%, how would community A nourish its beach? The idea that we might ask positive questions of what would we expect different communities that have different erosion rates, different tax bases, how would these two communities potentially behave differently? But ultimately, the art we might think about is what policy design would maximize property values net of investment costs, so net of the cost of investing in projects like nourishment or other types of infrastructure.
And a political scientist might start with the same normative questions, but we would move on to a different positive approach to those questions. Instead of looking at property values, for example, Marty.
Sorry.
We might look at, local public opinion and how that local public opinion translates into election outcomes, and how changing the composition of the voter base, right, by increasing the proportion of second homeowners, for example, how that would ultimately translate into local election outcomes. And the art for a political scientist might be a little bit thornier than the art for economics, because we often are attentive to multiple goals at the same time. So we might be looking for a policy design that simultaneously responds to majority preferences while at the same time protecting minority rights and representation.
So I want to share a little bit about cautionary tales from our experiences in interdisciplinary science and how it relates to what we're talking about today. So the first is just this idea that the failure to specify normative views often leads to confusion about which positive questions are important, and ultimately a never-ending proliferation of positive questions. So there can be many, many interesting questions, but scientists might talk past each other because they're not clear about what their normative views are or what the normative objectives are. Worse than that, though, is this idea of a leap of faith from science to policy, what we would call skipping the art. So you hear this occasionally in reference to, say, overfishing. Many fish stocks are overfished. That's an undeniably positive statement about the science. But the idea that that would immediately translate into, therefore, we should create marine protected areas in 50% of the oceans is skipping the art. Similarly, sea level rise will submerge much of the coast in the next 100 years. There's a lot of science to support that positive statement. But it does not necessarily translate into, therefore, humans should retreat from the coast. So now we want to talk about these two big grand challenge questions of seacoast that bring us together as scholars and practitioners and stakeholders, and diagnose a little bit about what's in these questions that's positive and what's normative. So the first question, how does the event recovery driven coupling between human and natural dynamics cascade through decades to alter risks and the resilience of communities, ecosystems, and landscapes? There is a lot loaded into this question. I've sort of highlighted in green what we would think of as positive questions. These are questions about how does this system actually work? This extraordinarily complicated system that links communities and humans and the decisions they make with the physical system and how it's changing. But embedded in this question also in red are normative ideas. Which risks do we actually care about? What does resilience actually mean?
And the same is true for the second question. what levers, actions of individuals, communities, governments, and other civil society groups enable mutual resilience of communities, ecosystems, and landscapes. There's a positive element to this question that requires us to understand the functioning of the coupled human natural system, to explain relationships between levers and outcomes, and predict those relationships out into the future. There's a normative element of this question, right? And it involves defining what mutual resilience means. How do we conceive of that idea, and what do we do with it? And then, right, that we're asking which actions enable or make possible the specified outcome, but what might prevent the lever from producing that outcome? That's that we have to be thinking beyond our immediate normative framework and beyond our immediate positive models to understand what might fear between these levers and outcomes. And as social scientists coming from these different disciplinary orientations, we're looking at these grand challenge questions, and we see this similar task in front of us as the Seacoast Project, right? We need to differentiate between the positive aspects of and the normative aspects, and we need to make choices among researchers, among communities, among the policy space and civil society groups, make choices about normative priorities in order, in some ways, right, most narrowly, to narrow the universe of positive research that we might pursue. The Seacoast model, right, has a co-produced research agenda that's going to have a strong community voice throughout to help us make these decisions. And we need to recognize the importance of both of these pieces in order to identify the levers that are going to help shape coastal futures.
So we'll leave you just with this slide of further reading to illustrate some examples of positive modeling in economics related to beach nourishment, positive modeling with some very specific normative implications, and then positive modeling in political science of beach nourishment. And then at the bottom there are also a couple of methodological readings. Now, obviously, Megan and I are in two different fields, but we share quite a lot of the same language and still have to work together to agree on what the normative objectives might be and how the positive questions fall out of that. So I think I just want to emphasize that our points of view, our disciplines are still quite close together, even though we've sort of juxtaposed our differences in this talk. And with that, we will take questions.
All right, thanks, Marty and Megan. We have a couple questions from the audience. This comes from Greg, and it's for either you or Megan. How do you bring in trade-offs that extend beyond the coast? For example, decision to spend money on beach nourishment versus investing in community redevelopment, for example, in Charlotte or Atlanta.
Maybe we can both. Go ahead, Megan.
So from my point of view, that's tapping two important questions, right? One is about defining priorities, right, which are mostly informed by the normative space. And it also involves defining the geographic scope, right? And again, as a political scientist, I think about the level of decision making and who gets involved in the collective decision making at these different levels. And as I think everybody on this call knows, right, the coast has been a place where there are different levels of decision making going on at the same time, and didn't reach the same decisions, right? And so what is that collective decision making? We might prescriptively think, oh, well, that authority should lie in a different space, but we need positive research to understand what the consequences are of the authority lying in these different spaces.
So I'll just add to that, the traditional economic view on this would be, well, you've got some public money that you could spend in one or the other of these places, So you would spend it where the benefit cost ratio is the highest, okay? But of course, now we've come to realize that that isn't necessarily going to lead to the most fair or equitable outcomes. And so we have to find a way of balancing those things. So if the benefit cost ratio is extremely different, we might think about still using that efficiency objective, but we might consider like whether there are really important other objectives that are involved in this.
Okay, next question. This comes from Reed. Megan mentioned collective decision making. I'm curious how this is defined broadly. How often is it met during some of the examples given?
I mean it in its broad sense, which is individuals coming together to make a group decision. And most often that's happening through political processes in which individuals come together and select representatives, and representatives through sort of a principal agent process, representatives delegate authority to agencies or to, you know, groups of bureaucrats or other entities to make these decisions. But I mean it in its broad sense, and we are translating preferences into policies at every stage, right? Policies aren't just a moment in time of enactment, but policies are the consequence of the enactment of a law and everything that happens subsequent to it. And there's collective decision making all the way through.
Okay, last question. This is for Marty or Megan. Can you again state the distinction between normative and positive aspects views in research? Just one last time.
So the traditional way of viewing this is that the normative is what should be, what should happen, how should we structure society or how have policy. The positive is really about what is. And so a lot of people would say that what we do in science is in the realm of the purely positive. But I think one of the things we wanted to get across here is that those distinctions are not always completely sharp, and the types of questions that we ask that we might say are purely scientific questions are motivated by what sorts of things you care about. So the value-laden aspects of what we are trying to achieve normatively influences those questions.
Okay, we have one follow-up really quickly. Reed asks, but in normative thinking, who decides what should be?
I'm going to punt that over to Megan.
So in normative thinking, right, individuals decide for themselves what should be through through everything that shapes how we come to know. Whether it's culture, religion, social peer effects, network effects, political elites trying to influence us, you know, what have you. But then it's through these collective decision-making processes where we translate that into some kind of social decision. And I gave precedence before, because I'm a political scientist, I gave precedence before to the sort of government mechanics for collective decision-making. But collective decision-making is also happening, you know, in those, and collective decision-making is happening in neighborhood associations, and it's happening through just coordination within a neighborhood or within unity through non-government processes. But people are that then have consequences going forward. Individuals' normative frameworks have to come together, and they have that collective priorities.
Okay. Oh, wow. There are a lot of responses to that. We have 1 minute left for Q&A for this section. It looks like Reed is satisfied with your answers. Tony wants to know, or her question is, what if even what is positively is different from perspectives of different stakeholders?
Wow, that is a really difficult issue. If to the extent that there's some objective reality that we're studying with science, if stakeholders misperceive that, that's a real problem for the functioning of our society. And I'm going to say that Megan is way more expert in this than I am because she works on climate change and public opinion. I've really set you up there.
Well, it was great because you set me up by saying misperceive, right? And that's assuming that there is an objective truth that we can know. There are spaces in which perhaps there is not an objective truth, and there are spaces, many spaces, in which there is an objective that it's difficult to know. Right, and our best hasn't determined what that objective truth might be, even if we believe it's out there. And so that might well lead different stakeholders to draw different positive conclusions without misperceiving. And so that does become part of the challenge. And I think it's a challenge that's even more present in interdisciplinary work, right? Because as researchers, we all come in with the biases that we have from the way our disciplines go about doing science. And that's going to lead us to a frame in which we privilege some forms of knowing over it.
Just to add briefly, I think it's still useful to at least know what we're disagreeing about. So if people have disagreements about purely positive questions, it's still useful to know that that's what the disagreement is versus people have different values and the normative objectives are different, and understanding that's what the source of disagreement is.
Okay, we have to switch gears. So thanks for all those questions. There were a couple more comments. We'll pass those along to the speakers. But now I'd like to turn over to Dylan McNamara. Dylan, you have to unmute yourself before you start talking.
There, you got me?
You're good.
Cool. Let me turn on my little, cool, and you can see that little red dot there? All right, yep. Awesome, thanks. Hello, everybody out there in Zoom land. I can see there's 80 some odd people out there, but I can see 5 faces, so I'm just gonna remind my colleagues to throw me some head nods, please, so I don't feel so alone. This is my first Zoom research talk, so you're gonna have to bear with me. I've had enough Zoom meetings, of course, to kill a person, but this is my first Zoom research talk, and I hope I can live up to the bar that Megan and Marty just set. I might not bring the personality that they did, but I have better pictures for sure. So what I'm going to try to do here over the course of the next 30 minutes is give you an introduction into some basic ideas in nonlinear dynamics. For those who know, you can see in the background there the famous Lorentz butterfly. I'll talk about that in a little bit, but I want to apply these tools, these ideas that I'm going to introduce you. I want to show you how we apply those to coastal settings like you see in this first slide. That is my hometown, Wrightsville Beach on the coast of North Carolina. I'm actually sitting in my house, which is about a mile to the left of that image there. I'd like to, of course, mention my co-authors too, Brad Murray, who many of you know, and also Zach Williams, my postdoc. He was very helpful in putting some of these slides together. So I think already you can, based on that first talk, when we think about this system from our own disciplines, it's very easy to say there's quite a lot going on. All kinds of processes in all different fields, geophysical processes, waves, currents, sediments moving around, economic processes, people buying homes, people buying second homes. There's social processes, there's mitigation happening as Marty and Megan were just talking about, beach nourishment, which many of you are familiar with, the construction of jetties and so on and so forth, ecological processes, political processes. So what I would like to ask is, and this is what I hope you can take away from the talk, is how is it that we can effectively consider the dynamics of these coastal systems on human relevant timescales in a quantitative way that gives us some insight into how the system is going to evolve. To get started in thinking about this issue, I'm going to do what a physicist typically does. I'm going to drastically simplify the system. So imagine Wrightsville Beach is a mass on a spring. Well, not really, but I do want to start with a really simple system to kind of illustrate some of the tools that are useful in nonlinear dynamics. This is a very simple mass, as you can see there, attached to a spring. The mass is sitting on a table, so there is friction between the mass and the table. And position x equals 0 is the resting position. And what I'd like you to do is just think about how that position evolves through time. This is a fairly easy system. We can write the equations down really simply. I'm not going to show them, it's not important. But if you solve the system of equations that govern this system, you get a plot that looks like that. So there is the position of the mass through time. We kicked it, gave it some velocity, and it oscillated and then settled down at 0 for all of infinity after that. So the important question is this enough to characterize completely that system? If you know x, do you know what state the system is in? And the answer is no. For example, if I told you x was equal to 0, you don't know if it's sitting there, you don't know if it's at 0 passing to the left, you don't know if it's at 0 passing to the right. So x is not enough information to completely characterize the system. You need some more information. In this case, velocity will do that for you. So there's a plot next to the position plot that shows the velocity through time. And it's doing a similar kind of a thing. Now, if you know x and you know v, you can say definitively what's going to happen in the future for this system. Okay? Now I'd like to expound on this by encouraging you to think about the fact that time here is not explicitly all that important, just in the sense that time's moving forward, right? I mean, as long as we're not moving at the speed of light or anything, time's just kind of marching forward independently. We can see that x is related to time, and we can see that v is related to time. Then, of course, x and v must be related to each other. So is there a way to collapse the information so that we can just see the evolution of x and v and have time be sort of an implicit piece of the story? And you can do that by plotting the behavior of this system in a very specific space called a phase space. So in this space, you've got x on the horizontal axis and v on the vertical axis. And you might not have appreciated that this shape was going to pop out for this particular system. So already you get some kind of neat, interesting insight into how the system's operating. Importantly, this phase space, again, is the axes that are necessary to characterize the system. This space is a treasure trove of utility. One great tool, for example, in this case is the fact that the spot 0, 0 is what's referred to as an attractor, a great name because it tells you exactly what it does. The spot 0, 0 attracts nearby locations in that space. So when the system started off here at this initial condition at time 0, it was attracted to 0, 0 in this sort of spiraling loop as it zeroed in on the attractor spot. Okay? And in fact, it's an attractor. It will attract any location from within this space, within reason, as long as I don't push the spring off the table or something like that. And just to illustrate that, if you solve the system of equations that govern this system for a different initial condition, instead of starting over down here on the lower left, we're now starting here, it again spirals in and then lands at 0, 0. So the attractor officially attracted it to that location. Another important thing about the phase space is there is an associated flow in that space. At every single point in that space, it's as if there's a road sign that tells the system where to go next. And they're uniquely defined. There's no forks in the road, importantly. Okay, so the flow is an important consideration here as well. So let's just increase the level of sophistication a tiny bit. I'm going to add a machine that just yanks on the mass on the outside. That's going to be denoted by that big black arrow, F, for forcing. I'll describe a little more explicitly what I mean when I say forcing. But for now, you can just think there's a machine yanking on the mass. What happens to the phase space behavior now? Similar kind of a thing. However, we have a new attractor. It's no longer the point 0, 0, it's a circle. It's attracting nearby locations in the space to the circle. Physically, what's happening here is the machine and the mass initially aren't kind of in sync with each other, but then eventually they get in sync and the mass just goes back and forth, which is a circle in this space. So that's an important thing to conceptualize and a very common piece of nonlinear dynamics. When you have an attractor, it depends on the forcing. If you change the forcing, you'll change the nature of the attractor and you'll change the nature of the flow in that phase space. Okay, so to take a step back for a second and just point out some of the decisions that were made in describing that system that were very specific. The system was defined by V and X, the two characteristics that were needed to describe the system, and the two pieces, importantly, that were coupled together, we would say, to use the jargon, which means V changes, the changes in V depend on X, and the changes in X depend on V. So they are intimately linked together. And we take a look in the space that captures those pieces, that's the phase space. There's an attractor in that space. And forcing was the thing that came in from the outside. So there was a sort of a one-way relationship. What F was doing did not depend on V or X. An economist would refer to as exogenous. That was an exogenous piece of the system. And then, of course, we saw, I'll just point it out again, that the attractor changed when you changed the forcing. In this case, we went from no forcing to a forcing, and we saw the attractor change. So now I'm going to increase and get into some real nonlinear dynamics 101, talk about a slightly different system to introduce some more complexity. This is a fluid, a two-dimensional fluid, being heated from the bottom. This is a pretty famous system. Here, if you're going to think about what's happening inside the system at a similar level of detail that we were doing the mass on a spring, sort of this Newtonian level of forces and accelerations and so on, it's quite complicated. There's heating from the bottom, fluid rises, it eddies, swirl around, there's turbulence, pieces of fluid slide against each other, there's friction in the system. It's extremely complicated. If you wanted to describe the system, the variables that you would need to get at all of those really fast time scale processes that I just described, it's quite complicated now. You've got to have velocities, the x-directed velocities at all of the xy positions in the fluid and through time, the y-directed velocities at all of the xy positions in time, the temperature at all the xy positions through time, and all the complicated nonlinear coupled relationships between all those three things. The equations, in fact, that govern that, the evolution of those variables, are very famous. For those who are familiar, those are the Navier-Stokes equations. Famous enough that if you can sit down and solve them with pen and paper, you still will win $1 million. It's one of the famous Millennium Prizes. Point being, it's really, really complicated. So the question is there an effective way we can learn something about this system without paying attention to this level of detail, this really fast time and small space scale? And there is. Anyone who's heated a fluid from the bottom knows that one of the things that you often see are these big convective rolls. So in some cases, the fluid behaves as if it's a collective at a level of description that sort of emerges at larger space and longer time scales. And I want to highlight again this idea, the reason I highlighted or bolded emerges is because this is the idea of emergence in nonlinear dynamical systems. Things that sort of have a dynamical description at a level that's distinct and higher than the faster timescale level. So what we can do is we can recast the description of this system. Instead of at those really refined levels, we can recast them at this larger space scale. And this was famously done by Edward Lorenz in the 70s when he was studying atmospheric convection. The essence of it is that he just reconfigured the Navier-Stokes equations, made some approximations to get out a system of equations that just had three variables that weren't X, didn't depend on X and Y, just depended on time. And I've kind of highlighted them here, T, V, and N. What they are in detail is not super important. I'll just kind of say quickly, T is a temperature difference between two fixed spots between two spots in the fluid. V is a velocity difference between two spots in the fluid. and N is sort of characterizes how nonlinear the shape of the temperature profile is, blah, blah, blah. It's not super important, but what is important is that they're sort of macro level variables, these emergent level variables. And what Lorenz had was equations that linked those variables together in a coupled nonlinear relationship. So you can very easily, especially if you have a postdoc, solve those system of equations and get plots. And if you do, for a particular level of heating, the plots will look like this. So the leftmost one is that T variable, the middle is V, and on the right is this N. One of the things that immediately jumps out, it's quite messy. And I hope you appreciate this messiness is entirely internal to the system. The flame's not flickering around. It's a constant heated temperature at the bottom of the fluid. All of that messiness is being generated internally to the system. And I'll just say that that was quite a paradigm shift for physical science, and it had ramifications in all kinds of different scientific disciplines. It used to be the idea that simple in, simple out, complicated in, complicated out. This was a case where it's relatively simple in and you get complicated out, which was pretty cool and surprising. But what I'd like to do is, as we did before, remove this explicit dependence on time and just look at the relationships between T, V, and N. So we can plot the behavior of this system in the same way in its appropriate phase space, where the axes are T, V, and N. And if you do, you get this. And for those who've never seen that transition, it's quite a thing. I mean, there's beautiful structure that was sitting inside that system that you would have never seen by just looking at those time series. This is the famous Lorenz butterfly. You could teach an entire semester about what's happening in this phase space. I'm not going to go into any of those details. But in our context here, we have a new attractor. It's not a point anymore. It's not a circle. It's this Lorenz butterfly shape. And that's all I'll say about it, because if I start talking about it, it'll take me 5 minutes. I'm not going to go into any of the details, but I want to go back and think about how we defined what the system was in this case and what the forcing was. So in this case, again, the system was the variables inside that importantly were coupled together. But here we made this increased leap where the variables that we focused on were these sort of emergent level variables. But again, they were coupled together. That's what defined the system. You plot it in the phase space, you get this attractor. And the forcing in this case was this one-way outside thing that didn't depend on what was happening inside the system, just the heat at the bottom. And just to show you, if you change the forcing, you change the attractor, you can reduce the flame, and boom, you get a different attractor. In this case, it whittles down to just a point. So you're starting off now in the phase space here, zooming around, and instead of getting caught in the butterfly forever, you just go to a spot. Okay, so if you bear with me for one more really simple system, a ball and a bowl. A physicist might call this a potential well, it doesn't matter. It's easy enough to think about it as a ball sitting in a bowl. Here, the attractor is the bottom of the bowl, position 0, velocity 0. What I'd like to talk about now is what happens when you, for just a moment, perturb the position of the system, perturb the ball from its attractor, give it a little kick. What happens? Well, in terms of what happens in its phase space, you give it a little kick from the 0, 0 spot, and it kind of winds its way back to the attractor, as we saw. But now, imagine you change the context a little bit. In this case, change the shallowness, make the walls of the bowl more shallow, not so steep, and give it a kick. Again, it comes back to the attractor, but importantly, it makes its way back to the attractor much sort of slower. And if you think about this from the standpoint of the flow in the space, now the flow, when you had steep walls, was much stronger and convergent towards the attractor. Relative to the case where the walls were shallower, the flow was a lot weaker and less convergent. So this is a really important consideration when you're talking about the stability of the attractor. How fast the flow gets you back there after you've been perturbed away. This is one side of the idea of resilience. Resilience is, in some contexts, once a system's perturbed, how long does it take to get back to the attractor that it was in before? Another aspect of resilience and stability is where's the edges of the wall. Of course, if you lower these edges, a given kick might send it over the wall and into some totally different place. That's another aspect of resilience. Okay, so just to recapture quickly, the tools that we just introduced, this idea of a phase space, attractors that exist within the phase space, and the fact that there's flow in the phase space, the idea of stability, how strongly convergent the flow is in the phase space. And then again, I just want to illustrate emergence, this time with a slightly more interesting picture. Classic emergent system, flock of birds. You know, there's a fast time scale level where birds are making really quick decisions based on what their neighbors are doing. But then there's this slower time scale, the flock level, where the dynamics are playing out on a longer time scale. And so when you're deciding how you're going to characterize the system, you have to make a choice about what time scale it is you're interested in. Are you interested in the bird dynamics really quickly, or are you more interested in the flock level dynamics? So now let's apply some of these tools to a location like Wrightsville Beach. So again, at very fast timescales, say seconds or minutes, hours, certainly in the ocean, there's really fast timescale processes similar to what we saw in the fluid, the convective fluid. There's turbulence and eddies and all kinds of things happening, waves breaking. In the sediment environment, there's sand grains blowing into the air, bouncing into other sand grains and doing all kinds of complicated things. In the ecological environment, there's very fast timescale things. Similarly, in the economic environment, I would say that there's very fast timescale things. People are spending money on a variety of things at different timescales with decision processes that have different timescales, deciding where to eat dinner, deciding where to go to the beach. But I think we can all agree that if you kind of smear your eyes a little bit, there are aspects of a place like Wrightsville Beach that exist on these sort of longer timescales. We can characterize the system on longer timescales. For example, the look of that beach, it's fairly narrow, pretty homogeneous. The look of that economy, it's a tourism economy. People are buying second homes, hotels are being developed. Those are kind of what I would view as the longer timescale aspects of the system. And part of the reason I feel like we can agree on that is because you can see aspects of that in systems all over the world. In the upper right, this is the Outer Banks, similar kind of an economy, similar kind of a beach. Lower left, California, similar economy, similar beach. In the lower right, that's coastal France, similar economy, similar kind of a beach. So it's suggesting that there seems to be this longer timescale attractor that the system is sitting in that involves things like beach nourishment and setting up a really dense tourism economy and setting up a particular kind of a beach. So this is what allows us to be able to define our system. The things that we focus on when we're thinking quantitatively about the system are things like patterns of sediment transport, pathways in sediment transport, not the individual sand grains, what they're doing, but more pattern scale sediment transport. And similarly in the economy, sort of pattern scale economic considerations in that tourism market. And then these two are coupled together, just like the velocity and the position were for the mass on a spring. They're coupled, they each depend on each other. The natural environment, what those sediment transport patterns look like impacts how storms hit the economy. And of course, the economy can drive changes in the physical environment through things like that we've talked about, beach nourishment, the enhancement of dunes. So that defines our internal system, all these coupled pieces. And then what comes from the outside are the things, the forcing pieces. There's a range of physical forcing, you know, things like sea level rise, that's going to happen regardless of what Wrightsville Beach is going to do day to day. You know, outside deep water wave climates, for example. There are economic forcings, things like what's the rate of inflation, political forcings, you know, presidential elections, things like that, that impact from the outside in sort of this one-way manner what's going to happen. And so just to quickly give you a sense of some of the things that we've done in taking this decision framework into numerical models. So we allow our decisions about what processes we put into the numerical model to be driven by these considerations of emergence. So we've done some previous initial work where we had a barrier island sitting on top of a continental shelf, and we sort of simulated those sediment transport pathways. We had an economic model that would sit on top of the barrier island, and we would simulate some of the economic processes on these longer timescales. Nourishment could happen in the model, storms would happen in the model. And just to give you a sense of what results pop out, we don't necessarily look at the attractor, but we look at characteristics of the attractor and how they change as the forcing changes. So this is just one plot. I'll speed through really fast. This is a case where we're looking at how long it is before the entire coastal town abandons. So people decide they no longer want to live there because it doesn't make economic sense any longer. And so what we're looking at here is the time in years to that abandonment moment as a function of how much it costs to nourish, what the nourishment sand cost is on the vertical axis, and on the horizontal axis, what the risk-free return is on investing in that property value. So you just think of that meaning that's just this sort of intrinsic property value. So, and it makes sense, right? Like if you go from left to right in the plot, towns tend to last longer, the attractor tends to last longer. If you go upwards in the plot and sand cost is getting more expensive, towns seem to not last quite so long. And of course, this was for one given forcing of sea level rise. We can explore others. One other quick result, we've done recent work inside grabbing data. So if you grab data, which my colleague Satya Gopalakrishnan, who's in the Zoom ether somewhere, I suspect, she's gone out and grabbed property value data for all these coastal locations that you're seeing here. And what you can do with that data without going into any details whatsoever is reconstruct the attractor, reconstruct the behavior in the phase space, and explore how convergent the flow is in that space. And when you do that, we've developed a metric, doesn't matter exactly what the details of the metric are, but this is a metric that measures how convergent the flow is. What we find is that in places that have lower levels of poverty, the phase space flow convergence is stronger. In places that have more poverty, the phase space flow convergence is not quite so strong. So these places are more stable, these places are less stable. And this is a result that jives with, I've seen pieces in the New York Times and NPR about this, but this is a quantitative representation of things that people know are happening in the system and allows us to kind of think then about, well, should that be? Why is that? What are the processes that are causing one to be more strongly convergent and more stable than the other? So we have an opportunity to quantify that. And then I'll just finish with, as Marty and Megan did, to talk about the grand challenge questions, but kind of recast them with the vocabulary that I just introduced. So the first question I would say is, how does event recovery coupling between human and natural dynamics alter the stability of this longer timescale attractor? And then what are the forcings? What kinds of political actions, economic actions enable an increase in the stability of this long timescale attractor? Okay, I have no idea where I am on time, but I'm done. So hopefully it's good.
You're doing great on time. Okay.
Take any questions.
We currently have limited questions oh, here we go. Deborah would like to know, with regard to forcing, is it possible for a system to resist or repel that forcing?
That's an interesting question. I think if it was possible to, if the forcing wasn't influencing the system, I guess I wouldn't call it a forcing. I don't know if Brad wants to chime in anything more beyond that.
No, I'd agree.
Are there
forcing sort of by definition is, forcing just by definition is that it's having an impact on the system.
Okay, thanks for explaining that. Are there any circumstances in which forcing would be considered to be inside the system instead of being exogenous?
I guess if I was going to call it forcing, it wouldn't necessarily be inside the system. But one thing to point out that's a pretty subtle idea is that as you increase the time scale, things that you thought were forcing at one time scale, if you go to an even longer time scale, those things typically become wrapped into the system. So if you go to longer time scales and larger space scales, so think about sea level rise. Yeah, Wrightsville Beach, sea level rise is a forcing on Wrightsville Beach, but communities as a whole across the world are certainly having an impact with sea level rise, and there's some level at which there's coupling going on there. So when you define it as forcing, it's very specific to that particular time scale.
So there's subjectivity in how you draw the boundaries around the system. It's a decision you have to make at the start of trying to figure out how the system works and what's forcing versus what's internal.
That's right. That's exactly right.
So you mentioned physical attractor in terms of position and velocity. So in what specific sense is the social attractor for coastal community resilience?
Oh yeah, great question. I don't have a real short answer to that. If the question is sort of what is the attractor, like the social, economic, political attractor? Again, it depends. You got to define a time scale. And I think what we'd say is that, at the kind of timescales that we've been investigating, these sort of yearly timescales, it has a lot to do with things like, property values is a significant piece of that. Yeah, I forget what the question was more explicitly. What were the social parts of it?
So in what specific sense is the social attractor for coastal community resilience?
Yeah, I don't have a really good answer for that one.
Okay, we'll get back to you, Victor. We have a couple more questions that came in. Is there an optimized solution to benefit long and short timescale attractors in terms of sea level rise on coastal dynamics?
Marty, you want to answer that one?
I don't have a good answer for that, but I do think that's a great question. And one of the questions we have to grapple with is whether such a reconciliation is possible. And I don't think we have an answer to that yet.
Okay. Well, let's do this one first. They're kind of linked. You talked about stability, one stable state. Can you talk a little bit about bistability?
Yeah, great question. So the systems I was looking at were relatively simple in the sense that they had in their phase space just one attractor, but it's entirely possible to have, for a given forcing, 2 attractors. And each attractor has associated with it a basin of attraction. So you could be sitting inside the basin of one and zoom down into that attractor. If you get a kick that's large enough, you get kicked out of the basin of attraction and then head to another attractor that's sitting in the phase space somewhere else.
Can you provide an example?
I think Laura would probably love to. She has a wonderful paper on bistability in coastal systems with respect to the shape of dunes. Laura, do you want to mention that one? That's perfect.
Sure, I can try to do that briefly. So dunes have a property which sets them up to either be low or tend to be high, because once you knock a dune down, you need a period of time without a high water event for them to grow. If you get a long enough period of time for dune growth to pick up, it actually happens pretty quickly. And so then you get a tall dune, which is pretty resistant to high water events. So there's a tendency for dunes to be either low, potentially, either low or high if the forcing conditions are just right. And so you can get a system that is kicked back and forth between a low dune state and a high dune state. So you have these 2 attractors with an intermediate state not being very, very common. And that, whether or not that system is bistable or stable at low or only stable at high, is going to depend on the external forcing and the conditions within the system as well. So interesting when you're in just the right situation to have that 2 basins of attraction be prevalent instead of 1.
Can I give another hypothetical example? That you could imagine that if we think of the present state of these coastal economies and landscapes as an attractor, potentially that's one stable attractor with Another one, in thinking of the ball in a bowl analogy that Dylan showed, with a ridge in between, and it could, I don't know what that other attractor could be, maybe uninhabited, maybe some very different kind of land use that, you know, we could imagine, but we don't really know. But as the forcing changes, physical, climate, economic, policy, whatever kind of forcing changes, the height of that ridge between the two bowls could shift, so that it could, just like in the dune analogy that, or the dune example Laura was giving, how easy it is to go from one of those stable states to the other depends on the forcing. And so as forcing changes in the next century, it's possible that we'll find that the current, what appears to be the single stable attractor, doesn't remain the single stable attractor.
The other thing I was going to say, not to beat it too much, but sometimes I wake up agitated and nothing's changed, but all of a sudden I'm just in my agitated attractor that day. Other days I wake up happy and I'm in my happy attractor, and nothing's changed. I just kind of wake up and I'm in some other part of the phase space and I find myself in my agitated attractor. That's another example. Sort of trivial, but relevant.
Okay, we have a couple more questions. Are there, or what are the physical implications from lack of stability in high poverty communities? For example, was there increased erosion in those areas in the modeling that you performed?
Yeah, so that's a good question. We haven't explored what the physical, some of the physical details of what the differences were. But I can just, the one thing I can just tell you, having lived through Florence, is, you know, seeing that in action. Wrightsville Beach was put back together really, really quickly. You could drive just a little bit inland from here to a less economically robust area, and they were not put back together very quickly. And I think a lot of us can think through a lot of the processes that lead to something like that. The difficulty in getting insurance for your house and your roof and all the paperwork and how you even find that paperwork and so on and so on. But in terms of the physical environment differences, we haven't really looked into that.
Okay, this question comes from Naomi. How do these systems change with multiple forcings? Must they be analyzed separately, or can they be integrated into a single analysis?
If I understand it correctly, typically the goal would be to do it in a single analysis. So once you decide on the timescale of interest and you construct, say, a numerical model at that timescale, often what is the exploration at that point is to see how the system responds as the forcing goes into different places. So in this case, more sea level rise, less sea level rise, more hurricanes, less hurricanes. And you just kind of watch how the attractor state of the system changes as you change those forcings.
Can I relate that back to the earlier question about optimal, I don't remember the exact phrasing, but optimal solutions? And to the degree that you sort of believe your model, if you've got a coupled model and you consider different policy options to be forcings, you can do an analysis once you identify what normative goals you're trying to optimize. You could then find which sets of policies would optimize those outcomes given possible different scenarios for the other forcings, like the climate forcings that you are less of interest to use as levers. So you could potentially use this sort of analysis to see how the forcings affect the optimality of the outcomes once you agree on those normative values.
Okay.
Can I just add to that really quickly? This is a really important question about how do you bound any analysis in this space. You have to draw the line somewhere in terms of what's considered. But if you exclude some external forcing that really matters, you might over attribute some other cause to the other external forcing that you are considering, or somehow that forcing might be more important and somehow offset by this one that you've left out. So I think that speaks a little bit to the art of doing modeling like this, and in that you need to make choices about how far to expand the scope of your system.
Okay, this is a far out question. Resilience has a connotation of being a good thing. Thinking just about nonlinear dynamics, are there reasons to consider resilience that is not necessarily desired?
Oh, a can of worms there. Scientifically, I try not to kind of put a judgment on, I like all attractors and all phase-space flows. I think it's not too hard to imagine that, speaking as a non-scientist, I guess, that certain very stable attractors might not be ideal. And they may be setting themselves up for a change that would be quite a bit more drastic than if they weren't so stable and were allowing themselves, say, the walls of the bowl to kind of move down a little bit in a fairly controlled way so that the system could be ready to sort of move to a different attractor a little bit easier without so much catastrophic change happening at one particular moment, I guess I would say, in a sort of loose way. Without putting any specifics on that. I don't want to call out any particular city or anything like that, but I think you can imagine what I mean when I say that.
Okay, we have two more questions. Is it possible to shift from one attractor to another based on internal dynamics alone? For example, without a forcing?
If you're in an attractor and there aren't external influences perturbing you from the attractor, you'll stay in that attractor. As long as the flow in the phase space is not changing, which it won't be if the forcing is not changing.
Okay, thanks for clarifying. And last question, can you talk a little bit about how one might use this framework, this modeling framework, to explore the effects of levers in the system?
Yeah, so I think we kind of envision those as like particular policies. Say, for example, like a change in insurance. Or there was an interesting article this morning I just glanced at quickly in the New York Times about this idea that now all of a sudden there's a lot of money being made available for buying out homes at the beach. So that's a policy lever that, if it's implemented, it would change the nature of it's kind of a forcing that would change the sort of evolution of the system and would change the stability of the attractor and potentially drive it into other places. Another example would be subsidies for beach nourishment. We've done some work to kind of show that when you change the amount that you subsidize beach nourishment, it really fundamentally changes. It's kind of a lever in the sense that it fundamentally changes what the stability of the system is, and what it gives you a new attractor basically that has sort of different details.
Oh, we have one more. Okay. Would it be possible, very, very quickly, to discuss the poverty levels on the stability diagram further by going back to the diagram? So really quickly, can you go back to that diagram?
Well, I can't remember what our dividing line was. Whoops. What our dividing, when I say low poverty and high poverty, I can't remember. Zach's out there somewhere, he would know. I can't remember the details. Wait for the paper, it's coming soon, and please read it. But I can't off the top of my head remember specifically what the differences were.
Okay, so Adelaide, we'll get back to you. So with that, we're out of time. If you could go to the final slide. Thanks for joining and for these thought-provoking questions. Our next Disciplines 101 session is 2 weeks from now.